Introduction to Verilog, Episode 1. This series is aimed at students studying digital system design. It will introduce Verilog for the purpose of configuring an FPGA. To keep the material accessible, an actual FPGA will not be used. Instead, you can either follow along with your favorite online simulator, or you can use the one at Tutorials Point. This episode will start by taking a few minutes to explain how Verilog fits into the bigger picture of using an FPGA. Then Verilog itself will be introduced. Greater emphasis will initially be placed on the simulation side of Verilog, and this is because Verilog was created for the purposes of simulating digital systems. Only more recently do people use Verilog for synthesizing digital systems within an FPGA. Principles of using an FPGA. An FPGA is a silicon chip that has got pins that connect it to the outside world. So you can take this FPGA and solder it onto a board and then connect these pins to external circuitry. An FPGA-specific piece of software is required both to create the digital circuit we want inside the FPGA and to connect that digital circuit up with the pins of the FPGA. That then allows the outside world to talk via the pins to our internal circuitry. To illustrate the process, first Verilog code is used to describe a digital circuit. The FPGA-specific software then creates this circuit inside the FPGA. Once we've described the digital system that we want inside the FPGA, the next step is to connect it up to the pins of the actual FPGA. This is done using the pin planner tool of the FPGA-specific software. Once that is done, then we can take this FPGA and put it in an external circuit, and by using the relevant pins, we can integrate our digital system into external circuitry. This video series will focus on using Verilog to specify the digital circuitry that we want implemented within an FPGA. However, part of the design cycle is verifying that the circuit is correct, and this can be done via simulation also in Verilog. Moreover, Verilog was originally designed for simulation, so in many ways it is easier to understand Verilog from the simulation perspective than from the synthesis perspective. Given this, we will therefore start by exploring the simulation side of Verilog. Verilog as a simulator. Hello world. When you go to Tutorials Point Online Verilog Compiler for the first time, you're likely to get a window that looks like this, with this code automatically populated here. To execute the code, you simply click on this execute button here. After pressing the execute button, and possibly after a few seconds, the output will display on the right-hand side and look something like this. The best way of learning is by experimentation, so you're encouraged to change the name of the module from main to Fred. So change main here to Fred, and despite this comment up here, it should actually work. After the change, press execute and check you get essentially the same as down here. And the other change you can make is you can delete line 8, delete this finish statement here and run it, and again you're going to get hello world printed out. When we hit the execute button, the Verilog simulator will execute module main. In fact, it will probably execute every module it finds, and it executes them in parallel because it is a concurrent programming language. And if you wish to test this out, then just delete the finish statement from each module, because as soon as the simulator encounters a single finish, it will stop and the unrun modules won't get run. Within module main is an initial statement. So initial, then it can be followed by a single statement, and that statement will get executed as soon as the module is run. In our case, we want to run more than a single statement, so we use a begin-end pair. Between begin and end, the statements get executed sequentially. So what will happen when you press execute, module main gets run, that in turn will call the initial block here, and first we will display hello world, and there it is down here, and then we will signal to the simulator that we wish to finish up, and so the simulator prints out that it's finished at time 0, and it was called from line 8 of main.v. In terms of syntax, note how the semicolon is used. We need one after the module definition, but we do not have one after end module. We also need a semicolon after each statement. So $display is a statement, $finish is a statement. We need our semicolon. Initial is going to be followed by a statement. In our case, we want multiple statements, so we have begin, end. So there are no semicolons after begin or end or initial. We could have initial semicolon, but then that's essentially a blank statement and it will do nothing. As an example of another way of using initial without begin, end, we could have done initial $display hello semicolon. Why do we have an initial clause? Well, Verilog is a concurrent language, not only between modules, but also within modules. So we cannot have a statement on its own. That statement must be triggered by something, whether it's initial or always or a sign, for example. We will talk about these concepts in due course, but for now, just accept that this is the structure we need in Verilog code. How does any of this relate to an actual simulation? Well, if we have a digital system, it's going to have some inputs that it receives from sensors or some external circuitry. Our simulation needs to generate the same voltages that would otherwise have been generated on these input wires. It also needs to monitor the outputs of our circuit, either displaying them or somehow verifying that they are correct. All this can be done inside an initial block. By having begin, end, we can have multiple statements in there which will be executed sequentially. The relevance of a display statement to simulation is that we either need to tell the user that the outcome of the automatic tests were successful, or we can tell the user exactly what the outputs of the circuit are. How to do the latter will be shown later in this video, and as an example, if we had some way of automatically testing our circuit and counting the number of errors, then at the end of it all, we can have if errors equals to 0, then display all tests successful. In either way, we want the ability to display something to the user. Verilog as a simulator, generating inputs and displaying outputs. The input to a digital system is just a time-varying voltage. This voltage in an ideal system is restricted to taking just two different values, 0 volts and say 5 volts. Verilog does not track the actual voltage, but instead it uses 0 to denote 0 volts and 1 to denote 5 volts. Any input, or more generally any junction in our digital circuit, is going to have a voltage. To represent that within Verilog, we can use either a wire or a reg. And remember, wires and regs will just take the values 0 or 1, but you should think of them as representing 0 volts or 5 volts. Whether we should use a wire or a reg is a finicky point with Verilog, but it's going to become clear later on which we should use in which occasion. It's best not to worry about it for now. If we were to display the value of a wire or a reg, then we really want to emphasize that that tells us what the voltage is at that junction. So if the value of a reg or a wire is 0, that would mean 0 volts, and if it was 1, that would mean 5 volts. Given a digital circuit, if we wish to simulate it, then we need to be able to generate a voltage waveform to feed into its input. This code is a simple example of just that. We have a junction called A, which later will serve as the input to some simple digital circuit. At time 0, module main gets run, the initial block gets run, so at time 0, line 5 gets executed. Line 5 sets the value of A to 0. A represents a junction in a digital circuit and 0 represents 0 volts. So this is essentially saying that the voltage at junction A is 0 volts. We need to keep the voltage at A equal to 0 for a period of time. This is where this delay statement comes into play. #1 means a delay of 1 unit of time. So if we're currently at time 0, then after #1, we're now going to be at time 1. So A will remain 0 up until time 1, at which point A is going to change and equal 1, which of course represents A changing to 5 volts. We now encounter a #2. This represents a delay of 2 units of time. So if we were at time 1, then after 2 units, we're going to be at time 3. So at time 3, the voltage at A changes back to 0 volts, and at time 4, being time 3 plus 1, time 4, at time 4, the voltage at junction A changes back to 5 volts. As well as generating a voltage waveform, we also want to be able to display one. Now, if we have access to a graphical Verilog simulator, it can actually graphically display voltages for us. However, with our online Verilog simulators, we need to resort to the old-fashioned way where we basically get our program to print out how the voltages change over time. The easiest option is to use a monitor statement. In our example, we have inserted a monitor statement at line 5. Whenever A changes, whenever the value at junction A changes, this statement is going to cause 2 numbers to be printed out. The first number is the time at which the change occurred, and the next number is the value of A. 2 things to keep in mind. This monitor statement starts a process that keeps executing in the background, and it monitors when A changes. So it's not executed once, so to speak, and then that's it. It gets executed, and then it creates this background process that can cause things to be displayed throughout our simulation. The second caveat, which will become more important later on, is that it's only going to display the final value of A at each time instance. For us, there's no difference because we only do one thing at each time instance. But if, for example, I had A is equal to 0, followed immediately by A is equal to 1, then only the A equals to 1 is going to be printed out because that's the last thing that occurs before time gets incremented. You should pause the video here and write down what you believe will be printed out when this code is executed. When we run the code, this is what gets displayed. And what causes this is this monitor statement here. The first column corresponds to real time, and the second column corresponds to A. Real time is an internal variable that records the current simulation time. A, of course, is the junction whose voltage we are changing here. Whenever the value of A changes, we get a new display. We notice that time goes 0, 1, 3, 4. Nothing was printed at time 2 because at time 2, A had not changed its value. From this output, we can therefore deduce that at time 0, A was 0, at time 1, A changed to 1, at time 3, A changed to 0, and at 4, A changed to 1. Of course, 0 represents 0 volts, and 1 represents 5 volts. Verilog as a simulator, adding in a simple circuit. This snippet of code corresponds to an inverter or a NOT gate. Think of a module as defining the behavior of a silicon chip. So my circuit is a type of silicon chip, one that we can go to the store and buy, and it's got two pins, one labeled A, which is an input pin, and one labeled B, which is an output pin. The relationship between the input and output is given by line 2. An assign statement is different from an initial statement. An initial statement is only run once. An assign statement is going to be triggered every time the right-hand side changes. So whenever the value of A changes, we are going to compute not A, or the inverse of A, and we're going to assign that value to B. Not once, but whenever A changes. This module has therefore defined a chip that behaves like an inverter. And just like we can buy multiple inverters, we can instantiate this module into our circuit many times. Module instantiation corresponds to buying this chip and integrating it into our broader design. So module main contains our whole design, so to speak, and our test bench code. We have now bought a single My Circuit chip. We have called this chip Fred, and we have instantiated or integrated it into our design here. To integrate it in here, we need to connect up its inputs and outputs to junctions that exist in module main. So in module main, at the top of the hierarchy, we've created two junctions, 1A, 1B. Because we're going to be changing the voltages at A, we declare it a register like before, and this allows us inside an initial block to assign it different values. We've created another junction B, and it's just a wire, not a register, because its value is not something we can directly control. Rather, the voltage at B is given by the output of our My Circuit chip here. For better or worse, I've called the junctions in main A and B by the same names as the pins here, A and B. We do not have to do this. So this A here corresponds to the first argument A here, and this, by its position, is going to correspond to the input A. Similarly, B is this B here, and by position, it will correspond to the B in my circuit. Intuitively, whenever the voltage at A changes, the value at B is going to change due to the fact that we've got this circuit now operating that modifies B whenever A changes. This is the output that the code produces. If we take for granted that we have integrated our inverter into our design so that B is the output of an inverter with A fed into it, then we can understand the output as follows. Our code here generates the input waveform A. As we've discussed before, at time 0, A is 0, at time 1, A is 1, at time 3, A is 0, and at time 4, A is 1. Now B is just the opposite of A. There's a NOT gate there. So whenever A changes, B should also change, and B should take on the opposite value of A. When A becomes 0, B becomes 1. When A becomes 1, B becomes 0. When A becomes 0, B becomes 1. And when A becomes 1, B becomes 0. Notice that in our monitor statement, we have added the value B as well. Technically, when either A or B change, we're going to get something printed out. But the only time B changes is when A changes, hence we still just have these 4 rows like before. What is the Verilog simulator actually doing? We can think of the module instantiation at line 9 as actually incorporating this circuit here into our main code here. In particular, we can conceptually replace this line with the circuit here. In other words, assign B equals not A. Now, because A went to A and B went to B, it is indeed correct to have assign B equals not A right at line 9 here. Had I had register C wire D and my circuit thread C, D, then this line would be replaced with a sign D equals not C. Since we now effectively have an assign statement here, then whenever A changes, B will be updated to be equal to not A. So once again, this is not something that gets executed once. This line creates a process to run in the background, and whenever A changes, B will be updated to remain equal to not A. Specifically then, as soon as A is equal to 0, then this detects that A has changed and B will be set equal to not A, or in other words 1. Then after 1 unit of time, when A changes to 1, the assign statement that is implicitly here will detect that A has changed and therefore update B again, so B will be equal to not A, and so forth. Some loose ends. Just to demonstrate the difference between the names of the inputs and outputs here and the names used in the main module, I have changed my circuit to have input X and output Y, and of course assign Y equals not X. In module main, I keep A and B, and this time I link in A and B with my circuit. This means that the A in main becomes the same as the X input to my circuit, and the B in main becomes the same as the Y output in my circuit. This matching is done by position. The first letter here is A, that goes to X. The second letter here is B, that goes to Y. This matching by position is not recommended because if I have many inputs and outputs, it's very easy to make a small mistake and get the order wrong somewhere, and then I've included the circuit in the wrong way. It is much safer to instantiate a module using this new style notation where we write dot and then a name of an input or an output, in this case .x, and then in brackets we put the name of the net is the correct word for these variables or letters here, A and B. We include the net that we want to connect to X in the brackets. So this says, like before, that the register A in main should be connected to the input X of the chip of type my circuit. And here we're connecting the net B to the input Y of the chip of type my circuit. The advantage of this is that I can swap the ordering of X and Y here and write .YB and .XA, and this will work in exactly the same way. So this no longer depends on the position of the arguments and is much safer. When we want to print out or display more than one net, it is safer to include a space between different values. And before, we explicitly introduced a space by using open quotation, space, close quotation. By just using a double comma though, we also get a space. So this is a shortcut that you might find convenient. If you run this code, you will get exactly the same output as before. In Verilog, because it is a concurrent programming language, it is often good practice to use different initial blocks to do different tasks. So whereas before we had one initial block doing both the monitor and the changing of A, here we have separated the two. When Verilog is run, it will execute both initial blocks at the same time. Now technically, if you're on a computer with multiple cores or CPUs and the simulator can use them, then you may well have both blocks executing at once. Usually though, the Verilog simulator will pick one to execute first. Importantly though, it will make sure that simulation time does not increment until all the initial blocks have done everything they need to do at the current simulation time. In particular, this means that if this first initial block were to be executed first, and we have A equaling 0 here, it is not going to go on and do a equals to 1 until the second initial block has also executed. The reason for this is that the #1 forces simulation time to increment by 1, and the Verilog simulator must finish everything it can do at time 0 before moving on to time 1. It is our job as a programmer to make sure that our code does not give different answers if it were executed in a different order. And we can check this with our current code here. Because our original code had the monitor statement first, if the Verilog simulator were to run the second initial block first and then the first initial block, we're definitely going to get the same answer as before. If it were to do the opposite and run the first initial block first, then we first get a is equal to 0, and then because this #1 is going to increment simulation time, the compiler is forced to execute the second initial block next, so we get a equals to 0 and monitor a. Monitor is designed to only print out the values at the end of each simulation time. And so whether a changes before or after the monitor statement is called, it doesn't matter. It will detect that a has changed and print out its final value at the end of simulation time 0 and before simulation time is advanced to time 1. Practice questions. Imagine in Verilog code there's the statement monitor, real time, $x, $y. Remember that the double comma introduces a space between real-time x and y in this case. Assume the following output is obtained: 000, 210, 511, 600, 701. Draw the voltage waveforms. So in particular, x and y are junctions in our circuit, and the monitor statement will print out their values every time x or y changes. It will also print out the simulation time at which x or y changed. The first column here corresponds to the simulation time, the second column to the value of x, and the third column to the value of y. You may wish to pause the video and try to draw the voltage waveforms corresponding to this output. Here we have the waveforms for x and y. At time 0, both x and y are 0. So at time 0, x and y are 0. They remain 0 up until time 2. So at time 0, at time 1, all the way up to just before time 2, x and y remain at 0. At time 2, x becomes 1, y is still 0. At time 2, x becomes 1, y remains 0. This continues up until time 5. So from time 2 up until just before time 5, both x and y keep their same values. At time 5, x remains 1, y becomes 1. At time 5, x remains 1, y becomes 1. Stays that way up until time 6, at which point both x and y become 0. At time 7, x remains 0, y becomes 1. You should try very hard to complete this exercise without looking back at the video until you really have to. Write the Verilog code to simulate the output of an inverter given the following input waveform. At time 0, the input is at 1. At time 3, it changes to 0. At time 5, it changes to 1. At time 6, it changes to 0. And at time 10, it changes to 1. This is very similar to what was taught in this episode. Try to write this code without looking at what we've done before, and only go back when you need to fill in the gaps. It will be the fastest way to learn. Here is the answer, very similar to before. First we define our inverter, then we define our test bench. We must include our circuit into our test bench using this module instantiation. We have bought a chip of type MyCircuit and called it Fred and wired A to its input and B to its output. The first initial block generates the desired waveform. The #3 here represents the delay of 3 units. So at time 0, A is 1. At time 3, A is 0. At time 3 plus 2 or 5, A is 1. At time 5 plus 1, i.e. 6, A changes to 0. And at time 6 plus 4, i.e. 10, A changes to 1. And lastly, we ask the Verilog simulator to print out the values of A and B and the current simulation time whenever A or B change.